Okay, let's dive right into a really big question, maybe the biggest. Where did everything come from? Right? The universe? The standard picture is the Big Bang Theory, which gives us this compelling idea of a single start, like 13.8 billion years ago. That's the one most people know. But today we're looking at something different, an alternative from Sir Roger Penrose, a brilliant Nobel laureate who also worked with Hawking. Penrose's idea is conformal cyclic cosmology, or CCC. It's pretty mind-bending, basically an endless cycle of universes. Exactly. It really flips the script on a single beginning. Our universe, our whole eon, as he calls it, is just one chapter in an infinite book. It expands out, gets incredibly dilute, and then through this amazing transformation, it sort of triggers the next Big Bang, like hitting reset. Penrose has these analogies, like the infinite encyclopedia, or a balloon inflating forever, almost infinitely big. And then somehow that super stretched out state, through this conformal transformation thing, mathematically becomes like the super dense start of a new universe, a new balloon. That's the core idea. Scale becomes kind of irrelevant at that extreme end. The angles, the geometry, are preserved in a way that lets it map onto a new beginning. So it looks the same mathematically as a hot, dense state. Essentially, yes, even though the physical size is vastly different, the end connects to the beginning, and that neatly sidesteps the whole singularity problem, that infinitely dense point in the standard Big Bang. That's one of the big motivations. It offers a potential way around it, continuous transformation, not an absolute start from infinity. So no true beginning, no final end, just cosmic recycling. Wow. It's a radical perspective shift, but how could you possibly test something so abstract, so huge? Well, that's the crucial question, and it leads us to these things called Hawking points. Hawking points are like fingerprints from the last universe, sort of leftovers imprinted on the cosmic microwave background, the CMB, the oldest light we can see, the afterglow of our Big Bang. The idea in CCC is that supermassive black holes from the previous universe evaporated away through Hawking radiation. That process happening at the very end of that eon should have left these tiny, faint, circular warm spots on our CMB. Those are the Hawking points. Imagine a beach at the end of time. The tide goes out, then our Big Bang is the new tide coming in, but maybe you can still see these faint, circular patterns in the sand from the old tides, waves. These patterns, these Hawking points, should have specific features. They're predicted to be circular patches, maybe 4 to 8 degrees across in the sky. Visually, that's roughly 8 to 16 times the width of the full moon. So noticeable patches on the sky map that are faint, incredibly faint, only about 5 to 15 microkelvin warmer than the background CMB temperature, tiny fluctuations. Penrose and his team predict maybe 20 or 30 scattered across the whole sky, and they actually claim they found some potential candidates in the Planck satellite data. That sounds huge, but I'm guessing not everyone agrees. Oh, definitely not. There's significant skepticism. Many cosmologists argue that these signals could just be random noise, statistical flukes in the CMB data, the old needle in a haystack problem. But a haystack the size of the universe and a needle that's almost invisible make distinguishing a real signal from random variations incredibly difficult, and that's where our current computers kind of hit a wall. Think about how subtle these things are, meant to be a few millionths of a degree difference, like trying to see a match lit on the moon. The CMB data itself is just massive, millions and millions of data points. So searching for these specific circular patterns with those tiny temperature shifts across the entire sky means a classical computer has to check potential spots one by one, sequentially. The number of possible circles you could draw on that map is astronomical. It takes forever. Plus, it's not just finding something that looks like a circle. You have to be sure it's not just random chance making that pattern precisely. The statistical analysis is hugely complex. How do you rule out false positives? And then ideally, you'd want to simulate the actual physics of the universe transition, which involves quantum gravity. Classical computers aren't built for that. They struggle with simulating those kinds of quantum effects efficiently. Supercomputers do amazing work analyzing the CMB, but for this kind of parallel search and deep statistical check, they have limitations. So we've got this fascinating theory, these potential clues, but our tools are maybe struggling. They're pushed to their limits for sure. So enter quantum computers. This is where things could get really interesting. How can these machines, based on quantum mechanics itself, help us find these whispers from before the Big Bang? Quantum computers work fundamentally differently. Remember the stadium analogy, looking for one face? Classical scans, row by row. Quantum computers, using superposition, can kind of look at all the faces at once, or at least vast numbers of them simultaneously. So searching the CMB for those faint circles becomes a different kind of task, a task they're potentially much better suited for. There are quantum algorithms like quantum convolutional neural networks, QCNNs, that are designed for pattern recognition in noisy data. They can leverage superposition to examine huge numbers of potential circular regions in parallel, instead of step by step. It's like having that detective who can check millions of spots on that cosmic beach all at the same time, which could speed things up a lot, like years down to days. That's the hope, absolutely, evaluating all possible circles, calculating the probability of them being Hawking points simultaneously. It offers a potential massive speedup. Quantum helps us find candidates faster, but what about the "is it real or just noise" problem? The cosmic coin flips? That's where another quantum trick comes in handy: quantum amplitude estimation. Amplitude estimation is a quantum algorithm that's really good at figuring out probabilities much faster than classical methods. It gives you a significant, a quadratic, speedup. So it could tell us the odds of a pattern being random noise much quicker. It's like running millions of random simulations simultaneously to see how often a pattern like the one observed pops up just by chance, helping us reach that high confidence level, that 5 sigma discovery threshold, potentially much faster. Getting that statistical certainty could become much more achievable in a reasonable timeframe. It also helps deal with something called the look elsewhere effect. If you look in enough places, you'll find something weird eventually, just by chance. Quantum algorithms might be better at properly correcting for that effect, giving us more reliable statistics. This is really cool. Okay, finding them, checking if they're real. But what about understanding the physics, simulating the universe transition? That's maybe the most exciting part. Quantum computers are naturally suited to simulating quantum systems. Classical computers struggle massively with that, like trying to model water freezing by tracking every single molecule. But a quantum computer is a quantum system. It can model other quantum systems much more naturally, and the universe transition is definitely quantum mechanics territory, plus gravity, a prime candidate for quantum simulation. You could potentially build a sort of universe in a box, simulate how particles, like photons, behave crossing that boundary between eons. Does their simulated behavior match the patterns predicted for Hawking points? Can we model information escaping those old black holes, things classical computers just choke on because the complexity grows exponentially? Quantum computers handle that scaling much better for certain problems. These simulations could really test Penrose's math, show if it holds up or maybe where it needs tweaking. And what about the black holes themselves, the source of the Hawking points, simulating their evaporation? That's another huge area. Black hole evaporation, especially the final moments, is where general relativity and quantum mechanics clash. It's a massive theoretical puzzle, the information paradox and all that. A quantum computer could potentially simulate those final stages like a virtual black hole on fast forward. Does the energy released match what's needed for Hawking points? So you could simulate the evaporation of those ancient supermassive black holes, predict the temperature profile, the size of the resulting Hawking point, and compare that directly to what we see or don't see in the CMB, a much tighter, more rigorous test of the whole CCC mechanism. This sounds incredibly powerful, but timeline-wise, when could this actually happen? Are we talking next year or decades away? Well, it's probably best to think in stages. Near term, maybe the next 1 to 5 years, you might see early quantum computers, maybe 50 to 100 qubits, which we're sort of getting to now, though they're noisy. The noise is a big issue, but you might see them running simplified pattern searches on small bits of the CMB data, like a proof of concept, probably hybrid systems, classical handling the big data, quantum doing specific calculations, a basic metal detector test. What about medium term? Getting more serious results? Medium term, let's say 5 to 10 years out, hopefully we'll have more powerful machines, thousands of qubits, and critically, much better error correction, fault tolerant quantum computers. Then you could potentially run full sky searches, apply that quantum amplitude estimation seriously to check statistics, maybe get close to that 5 sigma level for any candidates found. That's when it could get really interesting for CCC confirmation or refutation. Okay, 5 to 10 years for potentially strong evidence, and long term, that's really futuristic stuff. Long term, 10 years plus, who knows, maybe millions of qubits. That's where you could potentially run those really detailed simulations of universe transitions, black hole evaporation, the universe in a box, fully fault-tolerant machines running complex simulations for long periods that could potentially resolve deep theoretical questions about information transfer, energy conservation across eons. But huge challenges remain in scaling, coherence, error correction. It's not guaranteed. Still, the potential is mind-blowing. If this pans out, if quantum computers help confirm CCC, what does that mean for us, for how we see everything? It would be fundamental, a totally different cosmic story, not a single beginning, but an eternal cycle, like realizing the Earth doesn't just have one summer, but endless seasons repeating. And the question, what came before the Big Bang, gets an answer. The end of the last universe resolves that absolute beginning problem, and it resonates with some older ideas, cyclical time in some philosophies or religions, Hindu cosmology, some ancient Greek thought. There'd be a fascinating dialogue between this potential scientific discovery and those long-standing concepts. Scientifically, it would challenge the standard model, open up whole new questions about why the laws of physics persist across cycles. And even if CCC turns out to be wrong, if the Hawking points aren't there, or the simulations don't work out, even then, the effort would be incredibly valuable, developing these quantum algorithms, learning how to analyze cosmic data in new ways that pushes both quantum computing and cosmology forward immensely. We'd almost certainly make unexpected discoveries along the way. So it's not just about this one theory. It's about building new tools, new ways of looking at the universe. It forces us to sharpen our tools and our thinking, but getting there, you mentioned challenges. What are the big roadblocks still? Quantum error correction is maybe the biggest technical mountain to climb, making these machines reliable enough for complex science, developing the specific quantum algorithms that needs cosmologists and quantum computer scientists really working together closely, integrating quantum results with the massive classical datasets. The data integration piece requires clever hybrid approaches, and the theory itself, CCC, might need theoretical refinement as we learn more, especially about quantum gravity, plus we need robust validation methods. How do we cross-check and trust the results from these quantum simulations? Quite a list, it is. But the potential payoff, understanding our cosmic origins, is a huge motivator. So wrapping this up, quantum computers offer this potential new lens, a way to maybe see beyond our Big Bang, guided by Penrose's CCC theory, looking for those incredibly faint echoes, the Hawking points in the CMB static, and if they're found and confirmed, it rewrites everything we thought we knew about cosmic history, an eternal recycling universe. It would be one of the biggest discoveries in the history of science, answering questions people have asked for millennia. It really makes you stop and think whether CCC is right or wrong. Just chasing this answer with quantum computers stretches our technology, our understanding, opens up doors we probably can't even imagine yet. It leaves you wondering, doesn't it? What would an eternally recycling universe mean for how you think about time, about existence itself? Definitely something to ponder.